So we got about halfway through, maybe a little bit more than halfway through section 6.3 last time, talking about multiplication and division. And we ended up at a place where we're specifically, almost anyway, going to be talking about a specific type of multiplication. Before we do that, we have one more, two more examples that are related, examples 4 and 5. So we're going to talk about what we mean when we say 6 divided by 2 with a diagram, and then extend that into the next problem and talk about what it means to do 6 divided by 1/2. So there's a couple of different ways that we can describe 6 divided by 2. One of them lends itself very nicely to talking about division by fractions, and the other one doesn't really. So I'd like for us to focus on the one that actually lends itself well to talking about division by fractions. So we're going to break apart 6 into groups of size 2. So there's two ways to think about 6 divided by 2. You can think about 6 people and putting them in groups of 2, or you can think about 6 people and making 2 groups. You're with me? I want to talk about making the groups of size 2. So if I had 6 cookies, and I'm putting them in bags of size 2, then these 2 go in one bag, these 2 go in one bag, and these 2 go in one bag. And that would lead me to the answer that I would have 3 groups, all of size 2. So 6 divided by 2 is 3. It's often really hard to think about division by fractions because we're so used to our algorithm, which is the way we actually process through what we do, which is we flip and multiply, right? We flip the fraction upside down, we change the division to multiplication. But what did it mean actually originally the way it was written? Because if it didn't have any meaning, then we can do all the operations of flipping and whatever with no meaning, and that's like maybe fun and exciting or whatever, but it has no context surrounding that. And it actually does have context that I'd like to show you. So with this same idea, we're going to break apart 6 into groups of size 1/2. Now, it doesn't do a real good job to talk about taking 6 people and making them 1/2 of peoples. You can't do this with people. We can do it with cookies just fine, okay? So draw those 6 cookies again, like we did just a minute ago. Okay, so imagine these are the big giant cookies, like you'd get at McAllister's or City Bites, right? The whole cookie is definitely not 1 serving size, just saying. You and I may eat them in 1 serving, but they're really not. So you probably would share such a cookie if you were having some sort of an event. You might, in fact, even cut the cookies into pieces so that they would spread apart across more people. And that's the idea here, is that instead of having all my whole 6 cookies, I'm going to bag them up. And instead of bagging them up over here in groups of 2, I'm going to bag them up in groups of size 1/2. So I'm splitting my cookies apart. And if I do that, how many different servings of cookies do I now have? 12. I'll call them 12 groups, just like I did before. We kind of said loosely servings here just a minute ago, but we have 12 groups now. And if you take a look, that's exactly what happens when we take 6 divided by 1/2 and we flip the 1/2 and we multiply, right? Yeah. It's exactly what we're doing. So we're making groups or pieces of certain sizes. And you can think about it the same way for like pizzas. We do it with pizzas all the time. You take a whole pizza, you're not going to eat the whole pizza. My son came home and said he ate 4 pizzas at school yesterday. It's not what he meant, right? He meant 4 pieces of pizza, but that's what he said, 4 pizzas. So we take the pizza and we divide it into pieces, usually 8, sometimes 6, sometimes 10 or 12, depending on the size of the pizza. And we actually talk about how many pieces we would have if we divide it in a certain way. And that's what you're seeing happen here in this particular type of a description. Okay, so that actually ended the division part I wanted to talk about last time, but ran out of time for. So we're going to move on to talking about exponents. For a rational number a and a natural number n, a to the n is a times a times a n times. So I have n of these a's in a row, that's a to the n. And again, I hate to keep saying this, but for those of you who did number theory with me, we've seen some of these exponent rules back in chapter 3 before, but we're actually going to add to our repertoire of what we've got in this chapter. So there are 6 different theorems of exponents that I'm going to show you, and I'm going to explain why they each work. When you get to a test, or if you're in your homework, I'm not asking you to re-explain these. That is not my goal in doing this right now. My goal in doing this right now is to give you some exposure, so when that kid in your class says, but why? In the back of your mind, you're going to know, I learned this once upon a time and I can figure it out, or I can, resource something, I can Google it, whatever. There is a reason. It's not just because it works that way. It's really not a very satisfying answer for kids. So let's take a look at those 6 different properties for this that we're talking about. The first one is a to the m times a to the n. And in order to do that, we add the exponents and we keep the same base, a to the m plus n. If we have division, do you guys remember what happens to those exponents? Yep, we subtract them, a to the m minus n. What about when we have a power raised to a power? It's multiplication. And this last one, number 4, or the 4 that we had back in number theory, allows us to, it kind of feels like we're distributing. And we have a to the m, b to the m. We'll talk about why these work in a minute. 5 and 6 are new. We didn't have those in chapter 3 because chapter 3 is about whole numbers, not fractions. And now we do have rational numbers, which includes fractions. So we're going to talk about what happens when I have a fraction raised to a power. It looks a lot like property 4. I distribute that power to each the numerator and the denominator. And the only thing different between 5 and 6 is that number 6 has a negative on top. So it still distributes the power, but it also flips the fraction. So we have b to the m over b to the n. I'm sorry, a to the n. Like that. So we distribute the m part and we flip to take care of the negative. Okay, so I want to show you why they work. And I'm not proving this in general because I think that sometimes looks funny. And to be honest, I think that for the most part, your students will appreciate numbers where we've got letters more than doing it in general anyway. So we're going to do an example. So this is the rule that we're supposed to be trying to justify. And we're going to pretend that we have a cubed and a to the 4th. So what does a cubed mean? Right, a times a times a. And what does a to the 4th mean? 4 a's. 2, 3, 4. Okay? So somebody tell me, how many a's does that give me? 7. So this is a to the 7th. And how do you get from 3 and 4 to 7? You add them. Number 2 is the idea of subtracting. You guys are the ones who told me that one. Again, a justification by example. Let's say we have a to the 5th over a squared. What is a to the 5th? 5 a's. What is a squared? 2 a's. And Izzy had an appointment to get to, but she actually had the same idea on an earlier question that we talked about today. We see those variables. It's actually being multiplied by each other. We tend to leave that off when it's the variables doing that. But just like she talked about on that one, we are able, when it's the variables being multiplied, or if it were numbers being multiplied, to cancel like terms. So how many a's does that leave me with? 3, a cubed. And again, how do I get from 5 and 2 to 3? Subtract. Okay, let's do the next two. The next one said that I was supposed to multiply the exponents, so a to the mn. So let's do an example that is a to the third squared. So you guys told me a minute ago that a to the third is a times a times a. And when I square something, I write it down by itself. So it's a times a times a times a times a times a. It's written there twice. How many a's is this? 6. And how do I get from 2 and 3 to 6? Multiply them. Number 4 said I have the ability to sort of distribute the exponent to each of the factors. And we'll do an example with AB quantity cubed. So cubing something means multiplying it by itself. I've got it 3 times, just like that. These are all multiplied together, right? A's and B's, a bunch of them. So I can reorganize them and put all the A's at the beginning and all the B's at the end. And the properties that we're using to do that are the commutative property that says I can switch things around, and the associative property, which says I can regroup the A's together and I can regroup the B's together after I've manipulated and flipped them all around. And then, of course, we see what happens is I have A cubed and B cubed coming out of that. All right, the last two. Distributing over a division, a to the m, b to the m. We'll use the same cube that we used a minute ago. This justification looks just like the last one, really, maybe even a little more straightforward, because I have a over b, and a over b 3 times. I don't even have to regroup. I just use the properties of multiplication to multiply across the top. That's a cubed, and across the bottom, b cubed. Okay, you guys good? All right, the last one for this set of 6 says that a over b to the negative m flips it upside down to be b over a, and it distributes the power m. And we will do this same one that we had before, but we'll just make it a power negative 3 instead of positive 3. I don't want anything too big, not because I can't use it, but because it's not necessary to prove the point, right, to justify the point. So I'd kind of like for you to notice an interesting feature, and that feature is that negative 3 actually means that I could separate it to be cubed and to the power negative 1. So I'm sort of breaking the negative 3 apart into the negative 1 part and the positive 3 part. And the reason I'm doing that is because I already know what a over b cubed is. I just did it. It's a cubed over b cubed, right? We just did that and proved that. Now, the negative 1 exponent actually has a meaning. It means reciprocal. So when you see a negative 1, it does the reciprocal, and the reciprocal of this one specifically gives me b cubed over a cubed. That's its meaning. Well, its meaning is multiplicative inverse, but for what we're working with, that is a reciprocal. 2 additional fun facts that I'll justify as well. So do you remember what a to the 0 is? It's 1. I'll prove it to you in a sec. How about a to the negative n? 1 over a to the n, right? Yeah, good. So these are our 2 additional facts. I'm actually going to prove, like legit prove, that this works right here. You could put numbers in, but this one I think is simple enough to do either way. A to the 0. Well, a to the 0 is the same thing I would get if I did a to the m minus m. I mean, It seems weird to do so, but m minus m is 0, so I could replace it with something equivalent. If I use my properties sort of backwards, and I go back and look at property number 2, this means that I can put a to the m over a to the m, because the numerator, power m, minus the denominator, power m, would put me back where I just came from. But what is a to the m divided by a to the m? 1. Anytime you divide something by itself, you get 1. It might be worth noting that a can't be 0 to make this justification work. Obviously, my proof wouldn't work anyway because I'd just put 0 in a denominator if I did that. And in fact, 0 to the power 0 is undefined. We're not going to encounter it, but I feel like I should still say it. It's not working for a is 0. On the other one, I'll do another example one. We'll do the power negative 3. I like 3s. They're enough without being too much. So kind of like what we had done before, we'll separate the power 3 from the power negative 1. So we'll write that as 3 and then negative 1. And anytime you have a negative power, you flip the fraction. Well, this fraction is actually a cubed over 1 because it doesn't have a denominator sort of visible. So we end up with 1 over a cubed. All right, so everything that we do in example 6 and on and in your homework and whatever, you're not trying to prove to me why any of these properties work. You're just using the properties. Okay, your goal is to use the properties that you have now learned. So on this first one right here, part A, I have ab to the 4th over a to the negative 3rd, b squared. And there's often more than one way to do one of these problems, and they should all yield the same answer if they're valid ways of doing the problem. So for example, we notice that we have powers on 2 a's, that is an a in the numerator and an a in the denominator. One's in the numerator and one's in the denominator, so I could use property 2 and say that this is a to the 1 minus negative 3. And I could do the same thing with the b's. It's b is to the 4 minus 2. What is 1 minus negative 3? Yeah, it's 4. I actually have minus and negative, so it's positive. So this is a to the 4th. And what is 4 minus 2? 2, so I have b squared. So in an effort to save time, I'm not going to show you lots of other methods for doing this, but if you know other valid methods where you just shift things around based on powers and so forth, I suspect I'll show you another one of those here in a little bit. But this is one valid way to get to the proper answer. Notice all of your properties in sections, or not section, but 1 through 6 above, where we were combining exponents and so forth. Anytime I was able to combine things or separate things, it's because they had the same base. 2/5 and 4/25 are not the same base, right? They don't match. But I can change the 4 over 25 so that it would. So in particular, I'm going to leave my 2/5 to the power 3. And what I want to do is I want to leave this here as negative 6. I'd like to rewrite 4 as 2 to a power. What is it if I try to do that? 2 squared, right? 2 squared is 4. How about 25? How else could I write that one? 5 squared. And why do we like that? Well, we like it because the 2 and the 5 match the other 2 and the 5. That's the only reason. It's not because it's preferable, it just matches. Because they both have a power of 2, I'm going to go ahead and pull that 2 out with the negative 6 that's already out there. So this would be 2 to the 5th. And then what would I do? Would I add them? Would I subtract them? Would I multiply them? I mean, what would I do with the 2 that I'm pulling out and the negative 6 that's already there? What will I do? Add, subtract, multiply, divide. It's a multiple choice question. It's a good guess for adding. It's not addition. It's multiplication. It's actually property number 3. I have a power to a power. I have the power 2 on the inside, the power -6 on the outside. I'm going to multiply them together. So this is actually -12. The 2/5 now match. And I'm back to property number 1. Property number 1 says if the bases match and there's exponents on the outside, what will I do with my exponents? Add them. Thank you, Gracie. Yeah, I have 3 plus a -12. So what is 3 plus -12? Oops. Hope you're getting -9. Is that true? 3 and -12 is -9. Now, this answer is almost finished. Any idea why it's not complete? Yep, you're right, Brooke. Said that I'm supposed to have my answer at the very end, positive exponents. That's just the directions that we're given. And so when we get to the end, how am I going to make that -9 a +9 instead? We're going to flip the fractions upside down. So this will be 5/2 to the 9th. Please note, it's not asking you to figure out what is 5 to the 9th and 2 to the 9th. It's just wanting it in a reduced, simplified exponential form.
I'm confused how the -12, how you got there.
Because I multiplied 2 times -6.
But once you, okay, what happened to the bottom?
Okay, so 2 over 5 squared is the same thing as 2 squared 5 over 5 squared.
Oh, right.
So I simply thought of it like this instead, and then I multiplied the 2 times the -6. You bet. Paige.
So say when you did that, like say it was 2 squared and 5 cubed or something, how would you?
You wouldn't be able to simplify it in that way, and you'd have to just leave it as 2 squared over 5 cubed. Yeah. So this is working nicely because all the powers match to do that, but it's doing that on purpose. They're giving you those problems that way on purpose. Yeah. All right, let's do the next two. This one's asking us to actually solve for n if possible. So we are still going to be using the properties that we got, or we have 1 through 8 that we listed earlier. Notice on part A that 2 to the n and 2 to the 7th, the bases match. They're both 2's, right? So what can I do with the n and the 7? Add them. Yes. 2 to the n plus 7. Now 64 is not 2. I know, shocker, right? It's not, but we need it to be 2 in order to actually make progress in solving this problem. So what I really want is I want to rewrite the 64 so it's 2 to some power. And if you aren't sure what that power should be, your calculator can be used to do some guess and check. Try it. 2 to the 3rd, 2 to the 9th, 2 to the 8th. What does it take for you to get 64? It's 6. And again, it's just trial and error if you don't know off the top of your head what one happens to be. It's 2 to the 6th. So now notice, I'm not canceling the 2's, but I am ignoring them. They already match. The 2 equals the 2 as a base. So what that means is that in order for this equation to be both equal or equal on both sides, that means those exponents must also be the same. Not canceling the 2's, just ignoring them. Can you tell me what n would have to be to make this work? It'd have to be -1. Either by visually you just looked at it and no, right? -1 plus 7, 6. Or if you want, you can just subtract the 7 to the other side. B looks a little different for 2 reasons. Number 1, there's fraction. Number 2, there's a less than or equal to. So the less than or equal to simply means that that's going to be part of the answer. It's not going to affect the work or anything. But the 1 over 81 part will look a little different. I still need this to have a power of 3. So for right now, what I'd like to do is to just leave the 81 in the denominator, And I'd like to ask you, what would I have to raise 3 to get an 81? Okay, so we'll get to that in a second. How about, can I just do 4 for right now, Emma? Okay, so 81 is 3 to the power 4. Again, your calculator can play around with that, trial and error, until you figure out which one you need. But I need to compare them with one not in the numerator, one in the denominator, but they're both, at the same place, either both in the numerator or both in the denominator. So I need that 3 to the 4th to be 3 to what? The negative 4, right? I'm pulling it up from the denominator. I'm using that property number 8 in reverse is what I'm really doing, right? Using it backwards. The properties go forward and backwards. So again, the 3's as bases match. I'm not canceling them, I'm ignoring them. So it must be true that their exponents have the same relationship they would have if you consider them alone. N would have to be less than or equal to negative 4. All right, let's go to the next one. Number 8. I don't know about you, but I don't really want to divide 20 1/3 by 9 7/8 exactly. That would not be all that much fun. Kind of tedious and yucky. So I'm really glad the question actually asks for an approximation. Approximation does not mean plug it in your calculator and then get a whole number answer out of it. It's not approximation. Approximation means changing the values to make it easier to work with. So what would be close but easier to work with than 20 1/3? Y'all should talk to me. It's 20, right? I know y'all are thinking it. Nobody wants to talk today. It's 20. How about 9 7/8? What would be easier to work with than 9 7/8? 10. Can you divide 20 by 10 pretty easily? Yeah. So this is going to be approximately the number 2. Why is approximation important? Well, number 1, sometimes it's good enough. I don't really need to know the exact amount of money I need to give the cashier. I just need to be close, right? Sometimes it's good enough because it's valuable to do, because if I'm actually asked to work this problem out exactly, it'd be kind of nice to know if my answer looks sort of right or if it looks completely wrong, right? If I did this problem out longhand and I ended up getting the answer to be 20.7 or something like that, that's really off, because the expectation is it should be around 2. So it gives me some sort of a sense of what I would expect the answer to be. Okay, example number 9. Jasmine's reading a book. She has 1/4 of the book pages left, and she's read 246 pages. How many pages does she have left? Any idea about how you might think about or go about solving this? Brooke?
So she has already read 246 pages. We also know she has 1/4 left, so that means she's read 3/4. So 246 is equal to 3/4.
Okay, so this is what you just told me, Brooke, right? 246 pages would be 3/4 of the book, because she has 1/4 left, so she's read 3/4. AK, what were you saying?
I would just divide 246 by 3.
Right.
And then that's
So we know that she has 1/4 left. So if we were to take the 246, which is 3/4 of the book, and divide by 3, that would actually represent the number of pages that she has also now read, which happens to be the question we were asked. So what is 246 divided by 3? It's 82. So the answer to this particular question is 82 pages. What if instead it asked you how many pages are in the whole book? Yeah, you could add that to the 246, right? So be very careful as you're doing problems that have context, that you don't get so carried away in like the computation part of it that you fail to remember what you're actually being asked to find, because it's really easy to do. It's really easy on this one to switch the 1/4 and the 3/4 in your mind, like she's read 1/4 instead of 3/4 or something as well. All right, our last example for today, number 10. Al gives 1/2 of his marbles to Jose. Jose gives 1/2 of his marbles to Isabel. Isabel gives 1/2 of her marbles to Letitia. If Letitia was given 4 marbles, how many marbles does Al have now? So this is a lovely example of working backwards. So we can actually start with Letitia. And how many marbles does Letitia have? 4. But she got all of those marbles from Isabel, right? But Isabel gave her half of what she has. So if Isabel gave Letitia 4 marbles, how many did she originally have? She originally had 8. Now, after she gave them away, she only had 4, but she originally had 8. Isabel got her marbles from Jose. But Jose only gave her half his marbles. So how many marbles did Jose have originally? 16 originally. 8 now, though, right? Jose only has 8 now. And then Jose got his marbles from Al. Al only gave him half his marbles. So how many marbles did Al originally have? 32. Originally. Is my answer 32 to this question? Okay. What's the question ask me for here? How many does Al have now? So he originally had 32. How many does Al have now? He has 16 now. 16 marbles, I should have said, sorry. So again, another example of making sure that we really answer the question we're being asked. Because we could be asked, how many did he originally have? We could have, but we weren't. Okay, so here's what we're going to do. In terms of group work for 6-3 or group work for 6-4, I find it more important in my mind that you have the time to do group work from 6-4. So I'm going to go ahead and assign 6-3 to be done and turned in on Friday. So you're going to do the group work on your own, or you can meet with one another, Success Center, all that good stuff. But you'll do the group work, you'll do the homework. We just won't do group work in class this time. Sound good? Awesome. All right, you guys have a great day.